Welcome to Unit 4 of Online Chemistry 101. Unit 4 deals with Chapter 4, and Chapter 4 in your text deals with compounds and their bonds. And so we are going to discuss this in detail in this unit. Before we get to compounds and their bonds, however, I want to review a little bit about what we talked about in the previous unit. So I am going to ask a handful of questions that are similar to the types of questions that I asked in the previous unit. In this case, I'm going to be talking about this atom over here on the left part of the slide. And you can pause again at various points and try to answer the questions yourself before I discuss the answers. First question is, what type of element is this? And you can pause if you'd like. The way to figure out what type of element it is to count up the number of protons. In this case, we have 4, 8, 12, 16, 17 protons. So if you look up which element has 17 protons, you'll see that chlorine is the atom with 17 protons. So this is a cartoon version of a chlorine atom. Next question. What's the electrical charge of this atom? Well, we just said that there are 17 protons, so there are 17 positive charges. And if you count up all of the blue dots, which are supposed to be electrons, there are 17 blue dots, or 17 electrons as well. So 17 positive charges, 17 negative charges. That means that as this chlorine atom is currently drawn, its electrical charge is 0. It's a neutral chlorine atom. Now we can ask the next question. How many valence electrons does it have? Well, valence electrons are the electrons in the outermost shell. So let's count them up. 1, 2, 3, 4, 5, 6, 7 valence electrons. Next question. Is it happy with 7 valence electrons? Now, I put happy in quotes, again, obviously, because the chlorine atom doesn't have emotions, but we can basically ask, does the chlorine atom prefer to be in this state? And the answer to this is no, because of one of the rules that we discussed in the previous unit. The rule is basically that atoms prefer to have their outermost shell either completely filled or completely unfilled with electrons. And the way that it stands right now, this chlorine atom has an empty slot in its outermost shell. So it does not prefer to be in this state. Next question. How can it fix this problem? Well, the easiest way to fix this problem would be if the chlorine atom could acquire another electron from somewhere else out there in the world. If it acquired one more electron, then it would have its third shell, which is its outermost shell. That third shell would be completely filled. And that's the state that the chlorine atom would prefer to be in. So let's fill in that. Let's steal an electron from somewhere else. Let's say that the chlorine did that, and it filled in its third shell in the outermost shell. And now this is the state that the chlorine atom prefers to be in. So next question. Now what's the electrical charge on the atom? Before we had 17 positive charges, and before we stole the electron, we had 17 negative charges from 17 electrons. But we have an extra electron now, so we still have 17 positive charges, but we have 18 negative charges because of the extra electron. So 17 minus 18 equals negative 1. So the overall charge of this chlorine atom is now negative 1. And so what you tend to say is that you say chlorine prefers, or if you want, you can say chlorine likes, to be chlorine with an electrical charge of -1. And this is typically how you write the electrical charge of an atom if it has a charge. In other words, if the charge of an atom or group of atoms is positive or negative, you write the charge as a superscript to the right side of the symbol. In this case, the charge is -1, and sometimes you can omit the number 1 if you want. You can just write chlorine with a little minus sign there. That means chlorine with a charge of -1. So the first thing that I want you to know is that the electrical charge of an atom is usually written as a superscript to the right side of the symbol, and that's what we're doing here. And I want you to realize that chlorine prefers not to be electrically neutral, but chlorine prefers to have an electrical charge of -1. And the reason is that it's trying to fill its outermost shell with electrons. So that's dealing with chlorine. Let's talk about a different compound now. So here's the atom, and I'm going to ask the same questions again. What type of atom is it? What element is it? Well, the way that you figure this out is you count up the number of protons. In this case, it has 4, 8, 9, 10, 11 protons. And if you look up which atom has 11 protons in the periodic table, you'll see that it's sodium. And the symbol for sodium is a little bit weird in case you're not familiar with it. The symbol for sodium is capital N with a lowercase a, so it's Na. I believe it comes from Latin, but there you have it. You're going to have to realize that Na is the symbol for sodium. So this is a sodium atom. Next question, what's the electrical charge? Well, it has 11 positive charges. It has 11 protons. And if you look at the way that I've drawn it right now, it also has 11 electrons, so 11 blue dots here. So 11 positive charges, 11 negative charges. The way that this sodium atom is currently drawn is that this atom is electrically neutral. Next question, how many valence electrons does it have? Well, again, valence electrons are the number of electrons in the outermost shell. In the case of this neutral sodium atom, it only has one valence electron, and here it is here. So, next question. Is it happy? Does it prefer to have one valence electron in its outermost shell? And again, going back to the rules from the previous unit, you would say no, it doesn't have a completely filled or a completely unfilled outermost shell, so it doesn't prefer to be this way. How can it fix this problem? Well, in this case, it could conceivably steal 7 electrons to fill up the 7 empty slots. But the easier thing for this neutral sodium atom to do is to actually get rid of this extra electron. Then it has its third shell completely unfilled, and the second shell is still completely filled. So the way that sodium prefers to satisfy the rule that we discussed in the previous unit is to get rid of this excess lone electron that's sitting there in the third shell all by itself. So let's get rid of it. Now it's gone. This sodium atom now has a completely filled second shell and a completely unfilled third shell. And this is basically how sodium prefers to be. Next question, what's the new charge of this atom? Well, we got rid of an electron, so we got rid of a negative charge. Now we have 11 positive charges, and we only have 10 negative charges from the electrons left over. So 11 take away 10 is going to equal positive 1. So the overall charge of this sodium atom is now positive 1. And what you would say is you would say that sodium prefers to have an electrical charge of positive 1. Sodium actually does not prefer to, sodium atoms do not prefer to be electrically neutral. And so the way that we would write a sodium atom with a positive electrical charge is we would write Na, which is the symbol for sodium, and then a superscript to the right would be the little plus sign saying that it has a positive charge. And in this case, we don't have to write the number 1, because if you don't write the number 1, the positive sign just implies that there's a charge of plus 1. So there you have it. Sodium actually does not prefer, sodium atoms do not prefer to be electrically neutral. They tend to be cations, which means they tend to be positively charged, and in fact, they tend to have a charge of positive 1. So let's draw that there. So there's our sodium atom, and it has an electrical charge of positive 1. That's what sodium prefers to be like. So this may seem like a lot of excessive detail going over these rules again for those two atoms that we just discussed, chlorine and sodium, but this is the beginning of the introduction of how atoms like to attach to each other. And I told you on the previous slide that chlorine likes to have a negative charge. Chlorine prefers to have a charge of -1, and sodium prefers to have a charge of +1. Because this atom prefers to have this charge and the chlorine atom prefers to have its own charge, they have opposite electrical charges, and these two atoms, when they have these charges, are actually attracted to each other, and they will attach to each other to try to cancel out their opposite electrical charges. When they are attracted to each other and when they attach to each other, they form something called sodium chloride, which you may or may not be familiar with. Sodium chloride is the chemical term, the formal chemical term for table salt. It's the salt that you put on your French fries and on whatever you may happen to use for food. So sodium chloride, and this is the formula, the chemical formula for sodium chloride. Basically what this means is there's one sodium atom and there's one chlorine atom, and they are attached to each other, which is why they're put right next to each other. And the reason there is one of these sodium atoms and one of these chlorine atoms is because sodium prefers to have a positive charge, chlorine prefers to have the opposite electrical charge, and they're attached to each other. So by following these simple rules that we discussed at length in Unit 3 and at the beginning of Unit 4 here, you can actually figure out which types of atoms will end up attaching to each other and how many of them will attach to other types of atoms. electrons. So in this case, we know sodium likes to have a positive charge, chlorine likes to have a negative charge. They will be attracted to each other, and they will very often form sodium chloride, which is table salt. So now we've had a brief introduction into understanding how atoms or groups of atoms might attach to each other. They can attach to each other based on whether they're attracted to each other because of opposite electrical charges. So there are a couple of punchlines that I want to go over at this point. First punchline is that many atoms normally do not prefer to be electrically neutral. People have a tendency to think that all atoms prefer to have a neutral electrical charge, but that really isn't true for a lot of atoms. If you understand how the electron shells prefer to fill up, you can actually figure out what the electrical charges that atoms will prefer to have. So again, all you have to do really is play the types of games that we were playing on the second and third slides of this section to figure out the preferred electrical charges of many different atoms. And then finally, if you can figure out what the electrical charges that certain atoms prefer to have, you can figure out the chemical formulas of many different molecules. You can figure out that sodium likes to attach to chlorine. And not only that sodium likes to attach to chlorine, but that one sodium likes to attach to one chlorine, because sodium has a charge of +1, chlorine prefers to have a charge of -1. And you'll see more complicated examples of that soon enough in this unit. The other punchline is that you might be able to begin to gain an appreciation for why the periodic table has this weird shape. We said that the first electron shell, the first shell that holds electrons, holds a maximum of 2. And if you look at the first row in the periodic table, there are only 2 elements there. What that is basically telling you is that the first row, if you had an electrically neutral version of a hydrogen atom, it would have 1 electron in the first shell. If you had electrically neutral helium, it would have 2 electrons, and both would fit in the first shell. But then if you needed to put more electrons into an atom, you would have to start filling in the second shell. And if you remember, the second shell has slots for 8 electrons. And if you look at the second row in the periodic table, there are 8 elements here. 1, 2, 3, 4, 5, 6, 7, 8. And basically the way to think about this is if you had electrically neutral lithium, the third electron would be the first electron in the second shell. If you were talking about neutral beryllium, the fourth electron in beryllium, in the neutral beryllium atom, would be the second electron in the second shell. And then you could keep filling in the second shell with a third electron, fourth, fifth, sixth, seventh, and eighth. And then all of a sudden you run out of space in the second shell, and so you start having to fill in electrons in the third shell, which is why the third row begins here with element number 11. And then you can fill in again. We said that the third shell also had space for 8 electrons, and you can see as you move across this row, there are 8 elements here. And then it gets more complicated in the fourth rows and beyond, so we're not really going to talk about that in any great detail. The other thing to point out, however, is to look at the columns. Every element in this column basically will have, if it's electrically neutral, if you have an atom in this column that's electrically neutral, it will have 1 electron in its outermost shell. So hydrogen will have 1 electron in its outermost shell if it's neutral, same with lithium, same with sodium, etc., etc. What this means is that if you play the game that we were discussing in the second and third slides of this unit, that all of these atoms will prefer to lose an electron, and they will prefer to have a charge of +1. That's the state that they prefer to be in. If you look at all of the atoms in this column, in the second column, which is called group 2, you will see that every electrically neutral version of each of these atoms has 2 electrons in its outermost shell. And the easiest way for these atoms to get into their preferred state is to lose those 2 electrons. And if these atoms lose their 2 electrons, they will have an electrical charge of +2. So the atoms in this column prefer to have an electrical charge of +2. What happens in the middle here is a little bit more complicated. We're going to discuss it a tiny bit, but we're not going to discuss it in great detail. What we will discuss, however, is the right side as well. Over on the rightmost side, these atoms here, they all have a completely filled outer shell. So these atoms over here actually prefer to be in a state where they are electrically neutral. So these atoms tend not to have any electrical charge. But if you move over one column to the left, these atoms over here have almost completely filled, but not quite completely filled electron shells. So as an example, fluorine and chlorine have 7 electrons in their outermost shell, but those shells can hold 8. So they have one empty slot, you can think of them as having. If they have one empty slot, they will prefer to steal an electron from someplace else, and because of that, the atoms in this column will prefer to have a charge of -1. The atoms in this column have 2 empty slots, at least for these 2 rows, and because of that, they will prefer to have an electrical charge of -2. And again, it gets a little bit more complicated in the middle, so we're not going to discuss that in great detail, but I do want you to know that the atoms in the first column prefer to have an electrical charge of +1, in the second column an electrical charge of +2. Here, these atoms in this column prefer to have a charge of 0, these -1, and these -2. So hopefully you're beginning to get an appreciation for why the periodic table has this strange shape to it.